Good afternoon, good morning, good evening, everybody. Thank you all for accepting our invitation to Qualcomm Showcase Unleashing the Full Potential of 5G. The year 2020 is a significant one for IMT 2020 or 5G in Africa for two key milestones. Firstly, the WRC 19 decisions to identify millimeter wave spectrum globally. And secondly, the anticipated timely finalization of the IMT 2020 recommendation, which, as we all know, is on course for later this year. Today, we want to bring you Qualcomm's perspectives of what it will take, of what is being done to realize the broad 5G vision, which is connecting billions of people, devices, and things everywhere during the course of this decade. It's my real pleasure to introduce to you Dr. John Smith, who is a Vice President of Engineering at Qualcomm Technologies, and who is the head of 5G research. John joined Qualcomm in 2020. He holds over 150 US patents and has been involved in the system design of a variety of projects focused on the innovation of wireless communication systems such as 3G CDMA, IEEE 802.11, 4G, LTE, and 5G. John's work involves taking advanced system designs from theory through design, standardization, implementation, and productization. So at the end of John's presentation this afternoon, we will have an opportunity for a Q&A sessions. And I request you to post your questions on the chat during John's presentation, and we'll field them to him. John, over to you. Please start your presentation, and thank you very much for joining us today.
Thank you very much, Elizabeth. So it's my pleasure to introduce today and discuss on the whole kind of potential of 5G, where it's at now and where it's going next. So next slide, please. Qualcomm has been leading mobile innovation for over 30 years. You may recall the very early works on digitizing mobile communication and the transformation from analog to digital communications. And the era of redefining computing, this transformation from desktop computing to smartphone computing. Well, with 5G, the growth is even larger because we're transforming industries, connecting virtually everything at the wireless edge. So as Elizabeth said, when we look more broadly at Qualcomm, it's really about transforming how the world connects, commutes, and communicates. Next slide, please. And the foundation to 5G leadership really is technology leadership. We start with the vision, identifying a problem or need, and where we establish the requirements. How can we actually make the system better? What is the end use case for people that we're trying to improve? And with invention, we invent new end-to-end technologies and system architectures. And the research teams are also involved in significant proof of concept demonstrations, where we deliver end-to-end prototypes and impactful demonstrations to show the value of the 5G cellular system. And with standardization, we drive end-to-end design with ecosystem through the standards process. So this enables the global deployment of cellular technologies and the interoperability in terms of working across all the regions. We also participate significantly in trials. So this is where we have over-the-air field trials that track the standardization process and also enable the ecosystem to converge towards rapid commercialization. And the final stage is commercialization itself, where we engage globally with network operators to deploy new features. And so when we look at this cycle of innovation at Qualcomm, it's really core to how we were founded, and it's core to how we continue to innovate in wireless. Next slide, please. So taking a step into 5G itself, when we were designing 5G, the target was really to enable a unified, more capable wireless platform. Just as LTE has continued to evolve over a decade of time, we fully expect 5G itself to continue to evolve to support new use cases, new deployment models, and leveraging new types of spectrum. But at the very early days of 5G, the challenge was to define and design a unified overall system, something that could efficiently support a range of services. So these could include not only enhancing mobile broadband, but also things like the massive Internet of Things or mission critical communications where we need to deliver high reliability and low latency for communications that used to only be feasible to do on wires, we are now doing in wireless, such as transforming a factory or ground robots or other sort of mission critical scenarios. At the same time, 5G also expands how we're able to use spectrum. So not only the low bands below 1 gigahertz and the mid bands up to 6 or 7 gigahertz, but also taking 5G into millimeter wave bands, for example, 28 gigahertz or 39 gigahertz. And the interesting thing as well is that this is being designed for shared spectrum, unlicensed spectrum, as well as obviously licensed spectrum. So 5G itself is designed to work across diverse spectrum bands. And the other thing that's incredibly important with 5G is lowering the cost to deploy it, enabling more disaggregated RAN solutions, more diverse deployment models. So when we look at the ability to evolve cellular networks cost effectively, one of the other core parts was to ensure that 5G itself could support a range of diverse deployments. So putting this all together, when we look at IMT 2020, the target KPIs that we're achieving with 5G include decreasing latency by a factor of 10, increasing the user experience throughput by a factor of 10, and of course, incredibly importantly, spectrum efficiency, how we're able to use the overall spectrum to have efficient communications. This can overall result in a traffic capacity increase of 100x and a network efficiency of 100x, as well as increasing the connection density by a further factor of 10. Next slide, please. So when we look globally at spectrum, as I mentioned, we have low bands, mid bands, and millimeter wave bands. And all of these are incredibly important to 5G because different use cases, different deployment models can all leverage different types of spectrum. And so what's interesting, as you can see here, is the role of the mid band and the millimeter wave bands and how they really, the low, mid, and high bands can all work together. So I'm holding in my hand here a phone that has 28 gigahertz and 39 gigahertz millimeter wave. And so the capabilities of getting very high data rates with excellent user experience is one of the advantages of 5G. And it's the fact that it's already commercially available now. As a point of reference, there's already now 80 operators with 5G commercially deployed, and 385 operators are investing in 5G globally. Even in 2020 itself, 200 million 5G smartphones are expected to ship. And if we look at 2022, that would be 750 million or more smartphones. And by 2023, 1 billion plus 5G connections. And so one of the points is that the transition from 4G to 5G is happening faster than the transition from 3G to 4G. And this is partly because 5G is playing such an important role for many different evolving industries, and also because with the pace of technology and the cost structure improvements, new deployment models, things like disaggregated RAN, new ways of virtualizing software implementations onto general purpose processing, all of this works together to enable widespread 5G deployment at a faster pace than 4G in its early days. And so when we look all the way to 2025, we're targeting 2.8 billion 5G connections. And this is only possible because of the global work on spectrum. So as OEMs and device manufacturers and chipset manufacturers and the entire cellular ecosystem is working together, we have this global snapshot of spectrum, where we have the ability to leverage the lower frequency division duplex bands, the FDD 600, 700 megahertz, but then also interesting opportunities at mid-band between, say, 3 and 7 gigahertz. And we also want to mention that these bands include, as I mentioned, licensed spectrum as well as unlicensed spectrum. And one of the huge opportunities is that 28 gigahertz band, or even more generally 24 to 30 gigahertz, where we see many different regions going after that millimeter wave opportunity. Next slide, please. So we look at, well, what is so interesting about millimeter wave? Well, one of the things is that in fact it can enhance and support incredible mobile experiences. So this could be rich multimedia entertainment, even augmenting the work with lower bands, where the devices will not only have millimeter wave, but also lower bands and mid bands, and they can all work together. And even more indoor capacity, as outdoor millimeter wave is offloading the lower bands, and massive bandwidth for cloud computing. As I mentioned, the aspect of how much computing power is within this device, that really showcases the transformation to the wireless edge. So what is the communication needs? What are the computing needs? And how are these intertwined? So with millimeter wave, we can have lagless experiences, things like multiplayer gaming or dense indoor and outdoor connectivity scenarios, as well as connected enterprises and fixed wireless access, where we're able to connect homes and small offices and businesses using 5G millimeter wave itself as a backhaul to those devices. So the ability for wired and wireless to work together, and for wireless to go where wired used to only be the solution. So with 5G, we're able to deploy for things like fixed wireless access, as well as mobile communication with a unified integrated deployment. This also enables 5G to enter interesting enterprise applications like factories. Next slide, please. So if we look at download speeds, a millimeter wave peak speed can exceed 2 gigabits per second with millimeter wave. And so this is the aspect of how we're able to drive communications to that next level. So at Qualcomm, whether it was our work in 2G, 3G, 4G, and now 5G, the ability to millimeter wave is an amazing technology advancement that is now commercially ready to be deployed. And so these download speeds with 5G and R are 5 times faster than LTE. So that can enable much more immersive communication opportunities. Next slide, please. So the other aspect about millimeter wave is how it can transform indoor enterprises, or even indoor and outdoor venues, whether those are conventions, concerts, or stadiums, or things like office rooms, meeting rooms, auditoriums, and transportation hubs with airports, train terminals, and subway stations. So really, 5G millimeter wave can be expanded both indoor and outdoor, and also with public and private networks. And so this opportunity to combine the low bands and the mid bands with millimeter wave is one of the core differentiators of 5G. Next slide, please. So I'm often asked the question, well, where is 5G? And the answer is it's everywhere. It's going to be something that is enabling not only wide area public networks, but also private networks where we're able to locally optimize deployments and delivering things like massive IoT and extreme broadband. And as I mentioned, fixed wireless access, providing that last 100 meters of communication directly to a home. And things like smart transportation, where 5G is being embedded into vehicles to enable communication both between vehicles and a more intelligent transportation fabric. Next slide, please. So the device I'm holding in my hand is a Release 15 standardization-based device. So when we look at 5G, it's going to play out in a series of steps. Release 15 is that foundational step. Release 16, and each of these releases lasts approximately a year and a half. The Release 16 is where additional content is added. So Release 15 was the mobile broadband focus. Things like addressing smartphones, connected computers, fixed wireless access, and expansion into venues and enterprises. So as part of Release 15, we enhanced that in Release 16 to expand it into ultra-reliable, low-latency communication. And taking 5G into unlicensed spectrum was part of Release 16. And new approaches for positioning and connecting vehicles, and even evolving the wide area eMTC NB-IoT technologies. And of course, we did not stop with Release 16, and our research teams are already now globally standardizing Release 17. So this continues further expansion into lower complexity, reduced capability, for example, NR Lite, or even taking extended and virtual reality into new opportunities, as well as furthering items like MIMO, communications, coverage, latency, and high precision positioning. And Release 17, of course, is not the end. There's already new ideas being proposed for Release 18, 19, and beyond. Next slide, please. So one way to view this expansion is to understand we're starting from the core, that core aspects of connecting cell phones, laptops, XR devices, automotive, and how we're expanding that in release 16, 17, and beyond into further industrial IoT applications, further spectrum usage, further ways of deploying private networks, and evolving millimeter wave and massive MIMO systems in mid-band. So that 5G expansion is something that is core to how Qualcomm views this innovation platform, that we start with a baseline and we continue to evolve it over a decade of additional opportunities. Next slide, please. A good example of that is our work in expanding 5G NR into unlicensed spectrum. And one thing to note is that in 5G, we're able to work in unlicensed spectrum, both in an anchored mode, that is where an operator could have some licensed spectrum, and then leverage additional unlicensed spectrum to aggregate or add up that data rate. But with 5G NR, we're also able to deploy standalone unlicensed, where you can deploy only in unlicensed spectrum without a licensed spectrum anchor. So this is very interesting because it unlocks more spectrum globally. It also introduces new markets and vertical opportunities and new deployment scenarios. So this is an example of a core area that Qualcomm has been researching for over a decade and something that now is part of the Release 16 system itself. Next slide, please. So we'll kind of peek into this NRU, or 5G NR and unlicensed spectrum, is an example of the bands, both in the mid-band sub-7 gigahertz, as well as the higher frequency millimeter wave bands. So as an example, in Release 17, we're looking at the 57 to 71 gigahertz operation of 5G NR. Whereas in Release 16, we enabled operation in the 5.9 to 7.1 gigahertz. So the fact that we're able to enable 5G to work in unlicensed spectrum as well as licensed spectrum is a great example of expanding how we're able to communicate and compute and leverage these technologies in a much larger number of deployment scenarios. Next slide, please. So then looking at a specific example, we would say, hey, what is the communication needs within a connected factory? Well, on one hand, we might have enhanced mobile broadband. For example, employees with head-mounted displays getting the latest access to blueprints or information they need to repair a machine or design an enhanced system. And how we can also combine that with things like computer vision that's able to process information spatially. Well, in a factory environment, there's also massive IoT where there could be many different sensors, whether it's monitoring humidity, temperature, vibration. And then combining that with things that need very low latency, such as automated guided vehicles or industrial robots, and processing that at the edge of the network with wireless edge analytics. So the reason we're putting all of this on one slide is to showcase, just as when we originally designed 5G, before the standardization even began. So going back all the way back to say 2014, 2015, we were saying, how can we design a system to efficiently support the combination of mobile broadband, massive IoT, and ultra reliable low latency communication? So that really was the challenge of the 5G system, to make sure we could support a wider range of evolving use cases and not encourage a single deployment to address only one of these three scenarios. So how could we have a 5G system that could enable a richer mix of different types of deployments and do it in a cost-effective way? Next slide, please. So a good example also is how 5G is evolving as a universal connectivity fabric for a smart transportation system of the future, where not only can we leverage the cellular network to have communications to vehicles, but we can also have direct communication between vehicles and other vehicles, so-called V2V, or vehicle to vehicle. This also includes vehicle to infrastructure and vehicle to roadside units, where we can have low latency communications that can improve driver safety, and latency sensitive use cases for collision avoidance. And we can also combine this with an overall evolution of smart cities and utilities. So when we look at the transportation framework and the ability of communications to improve that efficiency, it really is a good example of the continued technical opportunities that 5G and its evolution will bring. Next slide, please. Another example of the future relates to virtual telepresence collaboration. If we look at the processing that's occurring within the device and the processing that's occurring in the cloud, there's also a continued evolution of what is happening at the edge cloud. And things like boundless extended reality, where people are able to collaborate even if they're not physically present in the same room at the same time. So what is the information that needs to be processed by a pair of smart glasses, and how can that be exchanged with an edge analytics solution to efficiently process that video? So how can people see what other people are seeing and jointly work on a problem? And so this real-time insight into the evolution of communications and computing and human interface is also one of the very exciting areas of 5G, and that connectivity opportunity leveraging the overall enhancement in different ways that people can work together. Next slide, please. So when you look at the word IoT and the many opportunities of device types, it's important to understand the role of mobile broadband and low latency communication, for example, at the high performance end. But we're able to bring that into a mid-tier where it could be a wearable or a smart grid. So a lower complexity, lower power consumption, more moderate data rate, reduced capability NR light. Things like health monitors or industrial cameras. So with NR light, you're able to scale 5G into a lower tier of communication needs, devices that can last longer, but with more moderate communications. And when we look further at the low power wide area, that's eMTC NB-IoT is continuing to evolve. And that's something where it could be a low end industrial sensor or a smart city, agriculture sensors, utility meters. And even in 5G and R itself, over time, it will design for this lowest tier of wide area IoT. So with the 5G system, one of the exciting parts is that investment in the network is also something that goes hand in hand with enabling new types of devices over time. And so as people are coming up with creative ways of leveraging cellular connectivity, there's a whole range of new device types and new communication needs that can be optimized to handle it with just the right amount of power consumption and data rate and connectivity. Next slide, please. So when we take a longer term view of how I view the research driving into 5G evolution into longer term into 6G, it really is about this merging of worlds. We think of the physical world in which we, of course, all live, and the aspect of how we're communicating more and more with each other, with new types of devices and sensors. And so this physical world of communications is continuing to evolve. At the same time, that data is being digitized. And we understand the digital world, where some people will use the term a digital twin. So whether it's a twin of a factory or some automation scenario, the reality is there's a huge and accumulating amount of digital data. And the virtual world represents that immersive interaction opportunity, where the evolution of augmented and virtual reality is only going to continue with new forms of spatial computing. So when we look at the merging of the physical world, the digital world, and the virtual world, that really does represent new opportunities for human interface and human augmentation. So the best ways that technology can enable the most advancements for people across a wide range of scenarios. So whether it's improving healthcare, whether it's improving education, whether it's improving the overall wide area connectivity. Next slide, please. So when you put it all together, we've seen the 5G system. It's now commercially deployed in many different markets. And that began just with release 15. And we've had that continued evolution into supporting new frequency bands and new use cases through release 16, 17, and beyond. And as you continue to drive that advanced research, targeting the evolution of 5G into release 18, 19, 20, we're also looking at the longer term 6G opportunities. How the overall system is put together on this decade cadence of continued technology innovation. And so now we're going to begin a millimeter wave over the air demonstration video. So at Qualcomm, as we mentioned, when we're wireless innovators, it's because we invent end-to-end systems and we prove them out on our own research test beds well in advance of commercialization. So the video that's going to be shown to you today is from our research over the air 28 gigahertz test bed. Thank you.
Qualcomm has been investing in an outdoor OTA network and a headquarters in San Diego for a number of years now to push the technological boundaries of 5G. This is a 28 gigahertz system that represents a real-life deployment and allows us to understand and address real-life deployment issues. This was a network we showcased last year in MWC 19, but have since further enhanced to provide more robustness and coverage. It's a single cell deployment, single GNOB with multiple distributed remote radio heads that provide receive and transmit diversity, as well as fast beam switching across the deployment space. We've also enhanced it with repeaters, Qualcomm prototype repeaters, for non-line of sight coverage and out-to-in coverage. The test device on our network is based on the Qualcomm Snapdragon 5G modem RF system. We have 3 antenna modules for uniform coverage and experience for the UE. Throughout this demo, you'll be seeing this GUI that portrays the KPIs for the demos. We have the downlink throughput, the active and candid beams for up to 2 remote radio heads on the GNOB, as well as the active module and the associated beam pattern for the device. We'll be covering robust mobility, enhanced deployment, as well as new use cases on our network. With distributed remote radio heads, the GNOB has the ability to use multiple remote radio heads to different users or to a single user. We'll start off by showing the capability of spatial multiplexing. So using 2 remote radio heads to support 2 relatively close users without any interference to each other. We can also use these multiple remote radio heads to provide extra robustness as well as coverage for a single user. In this demo, we have a single user, again, being covered by 2 remote radio heads, walking towards a courtyard and briefly blocked by a metal van, but without any cut to service because of the other remote radio head. So this level of robustness is exactly what you would need in a real-life deployment, especially when you have a dense number of users or dynamics in the environment, such as in a big square like Times Square. So in this next demo, we'll have a user, again, being served by 2 remote radio heads, the same 2 remote radio heads, walking through a large crowd, dense crowd, and being periodically blocked from either side, but able to maintain the link and able to maintain the experience because of the multiple remote radio heads and the multiple antenna modules on the UE. We also want to show the limits of Release 15 as well as our own beam management algorithms. So the ability to beam switch and beam track our device. We put our device on a drone to have high mobility across our deployment area, as well as show high dynamics by showing rotation of the drone. We saw that even with a single remote radio head, we're able to comfortably support high mobility as well as the dynamics for, again, a uniform experience in the deployment. As we know, millimeter wave, it's hard to get non-line of sight coverage unless you have good reflectors in the space. So you're bound to have coverage holes in your deployment. We show that with our prototype repeater that we can actually overcome this line of sight diffraction loss and provide coverage and extend the coverage area. So repeaters are not only good for overcoming the diffraction loss of overcoming going around buildings, but also to overcome penetration loss going from outdoors to indoors. This would be key to provide any kind of coverage in an indoor space, lobby, cafe, or store where you have a high density of users and you want to provide data offload. We've also used our network to test new use cases such as boundless VR extensively to see that we can support the performance needed. We know that millimeter wave systems in terms of throughput and latency are perfect for these type of applications, but we also show that in our new deployment strategy with multiple remote radio heads, we can provide a level of robustness that are key for these immersive experiences. Thank you.
Well, thanks very much, John, for the presentation. And we are now into the question and answer session. I know we don't have too much time, but the first question that I have coming in from the audience is, those were really interesting concepts shown on the test environment. But we understand that there are already some millimeter wave deployments in the US. And the question is, what, if any, has been your real-life experiences with the networks and the ability for for services in millimeter wave, considering what we've just seen on the demonstration. Can you give us a comment on that?
Yeah, when we look at the millimeter wave deployments, that's one of the exciting parts that, for example, in the United States, several operators have already deployed commercial millimeter wave networks. And so when these networks that are already deployed, we're able to see those gigabit plus data rates. And it's something where the technologies, as shown in the video as well, are continuing to evolve. So already the deployments today are leveraging the fact that in many scenarios, the density of cell sites is already quite large. So whether it's 200 meters or 150 meters in many of these scenarios for dense connectivity, then millimeter wave can provide that incredibly high data rate experience and working hand in hand with the other bands. So what we've seen so far is very promising in terms of the data rates, and also, as mentioned a little bit in the video, the reflection aspect, that millimeter wave is able to fill those coverage holes based on reflecting off a wider number of surfaces. And so when we look at the data rate opportunities and the connectivity opportunities for millimeter wave, based on all the investment so far, it looks very, very promising, which is why we're continuing to see other operators also add in millimeter wave into their deployments.
Mm-hmm. Yes, there are actually two other questions that are interesting because they almost are discussing the intersection between technology and ICT policy. It's almost like, if you have a knife in the kitchen, it can be a weapon and it can also be a utility. So one question that's coming in is, if 5G is to be deployed in all aspects of our lives, at home, in the vehicle, do we risk individual liberty given government is able to monitor our movements, etc.? And I think, I'll let you have your perspective on that. But I think here is an example of where you have a technology, but it must intersect with appropriate ICT policies. So, but I'll let you, take that question. What are your perspectives?
Yeah, I think, Elizabeth, you make a very good point on the policy role as well. So with every technology capability, whether it's enhanced communication, enhanced computing, you can have a wireless sensor that's enabling someone to monitor medical data after they're discharged from the hospital. That can be incredibly useful in terms of, for example, preventing the need to go in for continued checkups. Instead, you can actually just get data that's at the appropriate speed that's monitoring certain things. So when we look at the overall technology opportunities, absolutely, privacy continues to be incredibly important in many different areas. And things like, the security of a 5G network is already enhanced with things like whether it's encryption or how we look at the overall security of the network. So the enhancements that were made as part of 5G itself. And even from Qualcomm, we have security that we call it an embedded root of trust, where deep within the silicon, that is the chip itself, we can have secure systems. And so security and privacy are always incredibly important as they intersect with technology opportunities. And when I view the broader 5G technical opportunities, I absolutely agree. It's important that things also occur in the best overall policy framework to ensure that the net balance of these new use cases and what they're improving is also done in a way that makes sense across these broader goals as well.
Mm-hmm. Yes, I have another question that's talking about, first of all, thanks very much for the presentation on millimeter wave. Now, this question is talking about the existing realities in Africa, meaning that there is existing unique challenges in the region, such as a high unconnected population, low ARPUs, and complex regulatory environment, lagging, etc. So I think when looking at millimeter wave, 5G, but also looking broadly, how you discuss the fact that 5G can be and should be deployed in low, mid, and high frequencies. The question is really trying to grapple with, can 5G is it appropriate? That's the first question. And second question that the gentleman is asking is that what steps maybe should be taken to ensure that the digital divide does not grow. So I guess this is calling in all the attributes maybe that you had on your presentation, in respect of the spectrum that can be used, in respect of of the being able to use FDD, TDD, all that, so that can this be deployed in a manner that will make sense to the realities in the African continent, basically.
Yeah, the technical capabilities of 5G, one of the core parts, even as we were designing it, was to improve the cost efficiency. So when we look at connecting the unconnected, and as you mentioned, the ability to leverage multiple frequency bands and the reason that the 5G network deployments can be less expensive is also because there's this global investment in new approaches for deploying hardware. And so this disaggregation of the radio access network. So the ability to bring in new types of general purpose processing, as well as opened interfaces for communication between nodes on the network. So when you look at improving the digital divide and improving connectivity, there's many technologies within 5G whose cost structures are also significantly improving. So things like integrated access and backhaul can enable those long millimeter wave hops to connect areas where there might not be wired connectivity. We also look at the role of fixed wireless access in delivering communications to a wide number of people, where you do not need to have then that wired infrastructure into each and every home. And so if we look at the ability for new approaches, and I mentioned the new deployment models, well, one of the core reasons and the motivations for those deployment models is to enable more cost-effective deployments. And so when we look at the cost per bit and connecting more people with more communication, then that cost per bit is substantially lower because of the technical capabilities. The fact that 5G is wider bandwidth, so a single integrated circuit can handle huge data rate, is something that also enables that same technology to be put to use on the network side. So for example, Qualcomm has RAN solutions where we're offering an FSM or a femtosite modem, a small cell modem that can efficiently support very high data rates. And that can be multiplexed across multiple users in some of these new dense disaggregated RAN scenarios. So when you look at the full set of 5G technologies, it's very important to understand how they can all work together, and the right choices at the right time for that deployment can significantly decrease the cost. And so when we look at connecting the unconnected, that global 5G technology opportunity is indeed very significant. And so in terms of the ability for the 5G core network, things like service slicing, the fact that a single network can support many different use cases and can have many different coverage profiles, data rate profiles, quality of service. So we have the ability to flexibly use the key attributes of 5G to address this scenario. So whether it's wide area IoT or even moderate data rates to a much larger number of users compared to incredibly high data rates to a small number of users. So the 5G system's able to adapt and scale across a lot of these trade-offs. And that's one of the core parts of technology, is putting those trade-offs in the hands of the engineers who can then design the most cost-effective deployment, and also across a wide number of devices. So not only can you have, yes, you can have a high-end smartphone, but also you can have a larger number of tiering of devices. And we've already seen 5G moving into some different price points, different numbers of devices globally.
Thank you very much. I think I've seen another question here. I don't know how we're doing for time.
Yeah, I can answer this one. It's a little bit about the aspect of 5G millimeter wave and how it can work with lower bands. So it's true. So millimeter wave in and of itself is not going to cover, huge numbers of square kilometers. It's really the fact that millimeter wave and sub-6 bands can work hand in hand together. And so when we look at the data rates and the coverage, so the different attributes of, say, 10 megahertz at 600 megahertz carrier frequency relative to, say, 20 megahertz or 40 megahertz or 100 megahertz at, say, a mid-band, whether it's a 2.6 or a 3.5 gigahertz, and comparing that, say, with 800 megahertz at 28 gigahertz. So the core part with 5G is how the different bands, different bandwidths and different frequency propagation environments work together. And so 5G millimeter wave is something that complements and works hand in hand with the low and mid band. And also 5G was something that could be deployed non-standalone, where it could even leverage the 4G core network and bring in the 5G RAN. And at the same time, 5G, of course, offers a standalone mode where you can have the new 5G core that has service slicing across multiple different implementation and quality needs.
Mm-hmm. Okay, thanks very much. And ladies and gentlemen, I think, you know, at the outset, what we had hoped we could do was to present to you the, should I say, the universe of capabilities of 5G technologies. And, you know, in these 40 minutes, you know, I guess we could just do a broad brush. But one thing which is clear is that the technological capabilities are there. And I think what needs to happen now is to marry that and use it to adapt to the local conditions. And I think one of the opportunities are for countries or for populations to innovate, you know, applications and systems that answer to local requirements and local needs. But, you know, I guess we've run out of time. I hope that John has given you an introduction of the wealth of technologies and the activities that are taking place. And we are available, I mean, for further questions, or even if you need more in-depth discussions of some of these concepts, and really look forward to interacting with yourselves on this subject. Thanks very much.
Thank you.
Mm-hmm.